Welcome to part 2 of writing microcode for an FPGA implementation of the 6502. I'm going to do a very quick recap of what we did so far. We already have an architecture implemented, which is here. This follows the original 6502's architecture, at least loosely, which is, as far as we know, it's this one. Not exactly, but close enough. Now, the microcode, what we're actually writing, is the control lines going here. So this is the load, which tells the register to get a value, or the bus enable, which tells the register to output the value. These are generated by the decoder logic, which is these blocks here, and can be roughly seen as the list here. Now, our architecture isn't 100% identical, so some of our microcode will be different, some of our control lines will be different, but they're still named under the same logic. The instruction, the decoder itself is a state machine, and it gets as input two things. The instruction register keeps the opcode we're currently executing, and the timing generation, which we call the instruction counter, tells us which cycle we are into the process. Sorry. The instruction itself, the instruction processing itself, always begins with two fetch cycles, and they're always implemented the same regardless of which opcode we're currently executing. The fetch cycles themselves fetch the program counter, which fetches the opcode we're executing, and the address immediately afterwards, whether the opcode needs it or not. Now, most opcodes do need that address, that data, but some don't. And for those, you may claim that this is a wasted cycle. I can defend this because of two reasons. A, it makes the design require less logic. And B, that's how the original 6502 did it. I'm guessing for pretty much the same reason. Now, to implement the code, we're using a test program that I wrote that is, it's supposed to go through all possible opcodes, at least almost, and in all possible modes, again, almost. Now, we have a recording of this test program running on an authoritative CPU. And this recording records the bus operation that the authoritative CPU did. So this is the address, and this is the data, and this tells us about the signals. In particular, 1 means this is a read, and 0 means this is a write. Now, so far, what we've implemented, if we measure it as in how deep into the test program we are, we read the reset vector and decide where the reset handler is. And then this sets up the stack, and we do that, and jumps to start, which we also do. And in start, we jump subroutine to flex dump, again, successfully doing it on our CPU. Flex dump dumps the processor status register onto the stack, which we implemented, and then starts conditional branching back and forth, which is where we fail, because we haven't implemented that part yet. This is the simulation. It compares our run against the authoritative version we got from the authoritative CPU. So it compares our CPU to the test plan, which is the recording. Okay, one last point. I use a bunch of external tools here, including all the code we're writing is available on a GitHub repo. There's a link to everything in the description below this video. So if you want to follow along, you can just check out the repository, and as we're completing opcodes, I will push them to the repo. So with that, I think we can finish the scripted part of the video and start the actual interesting part. So let's get coding, which means we close this and we jump here and we run the program, or actually the test bench, and we ask how far have we gotten? And we gotten as far as cycle 44, which is the 45th cycle, which means that we need to go here to line 45. Now, line 45 is executing the branch carry set. So that's the next opcode we need to execute. Cool. Okay. Step one, we want to check what that opcode is. So we go to the 6502 datasheet, and we go to the concise opcodes, and we can see branch carry set here as B0, which should correspond to what we're seeing here, B0. This one. Okay. Now, in theory, what we need to do now is go to the decoder logic, add this is a case on which instruction we're executing. So we're saying we want to compare it against an 8-bit hexadecimal value B0. And what we want to do here is handle op BCS. In theory, that's what we were supposed to write. Except the 6502 took a shortcut. Now, it took that shortcut in a lot of places. In most cases, I did not follow along. I didn't do that. But in this case, I will. And what I'm going to do is take advantage of the layout of the branch instructions. So let's look at all the branch instructions. We have branch plus, which is 1, 0. We have branch minus, which is 3, 0. Branch overflow clear, which is 5, 0. And branch overflow set, which is 7, 0. We have branch always, but you'll notice the dot here, which means branch always is a command added by the 65CO2. So we'll skip that for the moment. Branch carry clear 9, 0. Branch carry set B0. Branch not equal D0 and branch equal F0. So we see a very clear pattern of all the branch instructions are every second line in the 0 column. Which means that if we look at the binary representation, again the flickering. If we look at the binary representation of the instructions, what we see is if we look at F0, we see that the bottom bits are always 0. The top bit is always 1. Bit 4 is always 1. So the last bits are always 1, 0, 0, 0 for all branch instructions. And then branch plus branches if the 0 flag is 0. If the negative flag is 0. Branch minus branches if the negative flag is 1. Overflow clear, overflow set. Carry clear, carry set. Not equal jumps if the 0 flag is 0. And branch equal if the 0 flag is 1. So the next bit tells us whether we're checking for a 0 flag or a 1 flag. And the next two bits tell us which flag we're checking for. So you can actually take all of the branch instructions and decode them all together, which is exactly what we're going to do. So instead of handle op BCS, we'll do handle op branch. And we'll do that to all of them. So 1, 3, 5, 7, 9, B, D, and F. Let's sort this. Okay, so that's the setup. Our code is going to get called. Let's implement the actual So handle op, that's the most difficult part usually, finding where alphabetically it should go. Handle of op branch. Now, like I said, we get the instruction counter as an input to the state machine. So that's our case. And we treat any unknown state as invalid. This shows up very clearly in the simulation as everything turns red, which is what happens here. This way we can keep track of whether we reached an invalid state. And also execution will not continue from an invalid state. So that's the setup. Now, like I said, 2 fetch cycles are always handled the same. So we get at the first ADDR cycle. And here we need to begin coding. What do we need to do at this point? Well, if we look, branch carry set begins executing at this line. So it read in the opcode, which is B0. And then it read in an offset saying where to jump to, which is 0D. And because the carry was not set, it immediately followed on to the next instruction. So if the condition is not met, at this point, what we need to do is new instruction. Move along. How do we know if the condition is met? So the first thing we need to do is we need to make sure that we know which flags are set. The decoder doesn't know this right now, so we need to add that. So aside from, let's do it here, we want an input of 8-bit value, which are the flags, and I marks it as an input. Let's hook it up on the other end. We want not the top, the decoder, and in the decoder we want next to the control signal to say flags I get the processor status. Let's see if this is what I'm after. No, this is not what I'm after. This is the actual register, and it outputs its current control on reg p value. Reg p value. So if all goes well, we just hooked up the value so that the decoder can look at it. We can verify that this is indeed the case by doing an RTL analysis. So we already have one open, but it's out of date. So we hit reload. And we did not like it. Line 73. What's the complaint? Module decoder not found. We have a bug in module decoder, but it doesn't tell us what it is. Maybe if we minimize this and remove all of the things. Syntax error, line 34. Yeah, that should be a comma. Try again. This should disappear on its own. It did. Okay. Reload. Okay. Now, if we look at the decoder, we have the flags input, and that points at reg p output. That hooks to the flip-flop storing the current state. So that takes care of that. We now have access to the flags inside the decoder, and this is how I verified that I hooked it up correctly. Going back to the decoder, essentially, what you would expect at this point is that I do something like this. Case instruction register and grab the top 2 bits, so that bits 7 and 6. And then take the different options. So I want a 2-bit binary number 00, and that means I need to take the a negative flag. So I need to take flags I, CTL, I don't remember how I called it. Flags negative. Flag negative. That's what you would expect. But that's not what I'm going to do. The reason I'm not going to do that is because that will blow up the number of logic units I need in order to encode the decoder. Thing is, we're only looking at these 2 bits in this way if we're doing a branch. So what we will have is code that has to pick up all the bits. It has to look at all the bits of the instruction register, of the opcode, in order to decide whether to do this mapping. And the thing is, it's much simpler to do this mapping always and only look at them at the result if we're in the branch instruction. So instead, I'm going to do something different. What I'm going to do is we have logic condition flag, and we'll also do condition flags, and that's an array of 4 elements. This syntax is for system Verilog. For Verilog, I should have done 3 to 0, but system Verilog allows me to do this. Thank you. Now I assign each condition flag, so a 2-bit binary constant 00 is this. And then 0, 1, and the other. So if this is a 1, we look at the overflow. And if this is 2, we look at the carry. And if this is 3, we look at the 0. And then assign condition flag to be condition flags at location instruction register bits 7 and 6. This is called continuous assignment versus doing it inside a block, in which case it's called procedural assignment. So by doing continuous assignment that doesn't care whether we're executing a branch or not, I'm making the relevant flag available to me here without spending a lot of logic on doing the selection. This is much more efficient. So this goes away. There's just one problem. I may have used instruction register before you defining. No, that's fine. Okay, cool. So what do I want to ask here? I'm saying if condition flag is different than instruction register bit 5. So if bit 5 is clear, we're checking that the flag is clear. And if bit 5 is set, we're checking that the flag is set. And if they are different, then the instruction is done. We don't need to do anything else. We call new instruction. Let's see how that runs. Go back to the simulation. Regenerate because we changed the code. And now run to the end. And we have failed. Let's see why we failed. A address bus expected 40F2, received 40F1 on cycle 44. So go back here, test plan, cycle 45. Yes. Here's the thing. We didn't need the byte after the opcode, the operand. You're asking why not use non-blocking assignment operator. Wow, that's a bit. I'm afraid to go down that rabbit hole too deeply. Very, very briefly, there are very few synchronous operations here that just take values that are already calculated and store them in registers. And everything else, the rest of the code is all of it in asynchronous logic, preparing the control lines for the next cycle. So everything is using blocking assignments. Again, I won't go deeper into that because that's really, I'm going to lose half my people currently connected, I think. Tell me in the comments if I'm wrong. Where were we? Okay, so we were reading the opcode, and then we were fetching the first operand, and that was done automatically by the standard logic. But what the standard logic did not do is increase the program counter, because the standard logic doesn't know if the current opcode needs that operand. So we need to increase the program counter here, which we can do by saying control signals ctl I PC equals 1. This will increase the program counter, and hence the next fetch will be from F2 and not from F1. Let's see if that works. And what you really see here is the power of test-driven development. I did a mistake, and I didn't need to look for it. It just told me, hey, you're reading from the wrong address. Detected test start condition, and we didn't finish the run. Okay. We are at 46. We advanced 2 more cycles. Cool. So cycle 47 is executing this opcode, which is the branch carry clear. Now the branch carry clear does jump here and does work. However, it doesn't work. The reason it doesn't work is because this condition fails. The reason this condition fails is because the branch needs to be taken. So branch carry set succeeded because the branch did not need to be taken, and we executed new instruction. Branch carry clear failed because the branch needs to be taken. So let's talk about how we take the branch, which is not simple. Okay. So, the branch instructions receive a single operand, so a single byte operand. This single byte operand is treated like a signed integer and is added to the program counter, which at this point, I should remind you, was incremented already. So it points to the instruction after the branch. Okay. How do we do that? We do it with the ALU. The ALU is the arithmetic logic unit, and it has the ability to add two numbers. So it has A input and B input. B input can come either from the address bus low or from the data bus, and A input comes from the special bus. So what we can do is we can reflect now the input data, the data coming from memory, is latched in the data latch. And the data latch is hooked to the data bus ADL and ADH, but in the original 6502, not to the special bus. However, in my implementation, it is. So what we need to do is ADDR2 is, so first thing we want to do, we want to say the special bus source comes from a DLSB. Load the data latch into the special bus. So that's step one. Let's make sure it actually compiles. Yeah, so far so good. Step two, we want the current value of the program counter here. So what we do is we load the ADL from the program counter low, which we do with ADL source is CTL PCL ADL. The name of the signals is source destination. So this is a misnomer actually because it says increment, and in any case, in the original name, this wasn't an I, this was a 1. But I can't name a symbol with a name that starts with a digit, so I use I and O instead of 1 and 0. So, okay, ADL source comes from PCL ADL, and if we got it right, what we should be able to see here is we do the fetch, and then we should be able to see on the special bus 0B, which is the operand of the branch, and on the ADL address bus low, we see F4, which is the address of the next instruction we were supposed to execute. So that part worked. And the next thing we need to do is tell the ALU to add them. Now, the ALU does all operations unconditionally. What we actually want to do is tell the register after the ALU to latch the result from the sum, from the adding part, instead of the other logical operations it can do. So we want to say ADC, forgot the name of the variable, ALU op. So ALU op is CTL ADDS. That's called sums. Sums. And that is going to latch the result of the addition here, but it will only actually appear on the next cycle. So if we execute the code, of course after compiling it, we see that ALU result gets FC, but it gets it in the cycle after we set the ALU op to sums. which means that for this cycle, we're done. Now, this deviates from what the 6502 does. However, for reasons I won't go into, I'm actually preparing a video explaining them. We only care about cycles where we do an external bus operation. So at this point, the fact that we're taking an extra cycle is fine. It won't fail the test, and it's fine. So in this cycle, what we need to do is store that in the program counter. So we need to so we need the ADL to come from the ALU result. So ADL source should be ADL ADD ADL. I'm not sure I got it right, so let's check. So ALU op is sums, and the next cycle we should see address bus low being F4. No, that should be F. No, I didn't get it right. ADD ADL. The ALU result is okay. We need to make sure. I forgot something about our implementation, so let's check that. ALU generator, no, that's the ADL generator. ALU unit result goes to a result, and the output goes to SB inputs and ADL inputs on 0, 0. Okay, so yeah, that should have been correct. The input comes from result O. Okay, let's look at the actual code. ALU op. Yeah, so the ALU unit outputs the correct one based on the op. And the ALU itself sums does the sum. Yeah, so that should have worked. Let's see why it didn't. The ALU source was I didn't set ALU B source. That's why it didn't work. Okay, so up here, ALU B source is we want ADL. We want the ALU B source. Okay, this register has several options of where it gets its data. It can get from the ADL, it can get from the data bus, or it can get from the database going through an inverter. And we want the B register to be input to be from the ADL. I didn't tell it what, so it got X's, and X's with combination, adding X's to a value gives us X's, which is the reason why ALU result was X's. So run again, fix the errors. Forgot the CTL namespace. And this time we got the ALU result, and we got the address bus low to be F1. PCL ADL. Okay. Let's say again, ADL source is ADD ADL. Do we have ADD ADL as address bus low source? No. Why not? Which cycle are we on? We are on 4. I didn't finish the run. Oh. Okay. Come again. Address bus low gets FF, as it should. So far, so good. Next thing we want to do is we need to load that into the program counter. Now here, this area is how you do it on the 6502, but this area is actually implemented differently in our design. So what we want to do is PCL let's look at the actual code. So we have ADL PCL, and that's to PCL select. Okay, so that's how we do it. We go control signals, ADL PCL is 1, which means instead of using the previous value of PCL as a reference, load whatever it's on the address bus low. And at this point, we can just also do new instruction. The program counter was updated. We can continue execution. And the execution will continue in the new location. We got to cycle 46, so we didn't advance much. Let's see what we have. The instruction counter went back to fetch 1, and we fetch from 40FF, which is what we should have done. So far, so good. Why did it fail us? Too many cycles since bus operations on cycle 46. We took too many cycles to do this. 1, 2, 3, 4. Yes. Let's see if that is avoidable. This is not a bus operation. This is not a bus operation, and this is not a bus operation. So instead of fixing the code, I'm just gonna fix the test and tell the test that 4 is okay instead of 3. That's the simulation top. Too many cycles. Max cycles per bus. Set it to 4. And we got as far as expected 40F4, received 40FF. Okay, My bad. So what happened here? What happened here is we needed time. That was a mistake on my part. 3 is fine. What happened here is that we needed time in order to perform the ALU operation. That's why we took 4 cycles between bus operations. The thing is, the 6502 also needs that time, and during that time, it performs a dummy read from the program counter. So instead of reading, let's go over the branch carry clear. So it reads the opcode from the 40F2, and then it reads the operand of the jump location from 40F3, and then it reads another byte, which it never uses, from 40F4. This cycle, which it does not do if the jump isn't taken, notice, this cycle is so that it has time to perform the ALU operation. So all we need to do is, during the time we do the ALU, also output the program counter, which was already advanced. And this time we got quite a bit further. We were at 44 the last time. Now we're at 53. So let's see what are all the operations we successfully implemented. We were here. We did the branch carry clear, and now we've successfully jumped to 40FF, where we did branch minus, which we successfully not take. And then we did branch plus, which we successfully took to 41F4. No, sorry. And that's 54. That's the cycle we got wrong. Okay, what happened here? Why did branch plus fail us? So branch plus is at 410401, and it has a relative jump of F1. Now, F1 is a negative number, which in itself is not a problem, because we're doing 8-bit arithmetic. F1 would decrease the value of program counter. So that's fine. The problem, however, is that this decreasement needs to update the program counter high. So we're at 4102, and we need to jump back, I think that's 14 values, to 40F4. But if we update only the program counter low, we're going to get 41F4, which is indeed a read that 6502 does. It actually reads from there, it just never uses that value. So what happens is, if we need to jump over a page boundary, the addresses that have a shared high byte are called a page. So every 256 addresses are a single page. If we need to jump over a page boundary, we need to update the PC program counter high value. And that actually requires another cycle because it needs another ALU operation. So let's do that. So now the new instruction isn't automatic. What we want to see is that if the flags that we got from the, what we want to see is the ALU carry. The ALU has a carry out flag as well as an overflow out. And this carry out tells us whether 8 bits were not enough in order to represent the operation we just did. And we do have an input called ALU ACRI on the decoder that receives this value. So we're doing if ALU ACRI is set, sorry, if it's not set, then new instruction. Then we're done. Otherwise, we need to update program counter high. So, okay. Let's start with, no, okay, let's update, let's talk about that. So, else begin. How? Okay, before I begin, I want to make sure that I have this value at this point. So I want to track ALU ACRI. Don't think I'm tracking it right now. No. Am I tracking the ALU? Let's track those. Okay. The way I add signals here is I go here and I ask for the ALU unit. And the ALU unit, so these are all the values both inside and out of the unit. And we're looking for the carry O. Let's put it next to the ALU result. And now if we rerun the code, we can see where we know what the carry is. So this is the cycle when we're actually doing the operation, and that's not where we want it. We want it at least the cycle after. So the way to do that is to store it in a flip-flop. So we have ALU ACRI. We'll add a register called logic ALU ACR. And on the synchronous parts, we can say ALU ACR is ALU ACRI. This is called the non-blocking assignment, and it happens only when a clock happens, which means that if we now check here ALU ACR, we're going to get the value at the correct location. So, recompile. And now we are on. I need to start marking the cycles so I don't lose track every time. The fetch instruction ADDR3. This is, we do ADL add, sums. We get the ALU result here, and we're not checking, but the carry is set here. And why did we fail again? Pin address accepted 40F4, received F1, F5. 40F4 is just making sure we're on the right cycle 53. 40F4. Right. So we got this cycle correctly. We got this cycle correctly, except we kind of stopped here. So the first thing you'll notice is that for some reason the carry is 0. We're adding the B source. The B input is 3, and the A input isn't listed here. But the address bus low is 03, and the special bus is F1. Okay, So special bus is F1, and this is 0, 3. This is not the values we were supposed to be getting at this point. 0, 1, 0, 3. I see discrepancy between the cycle it claims we got to time 1145000. 1145000 is here. We do a fetch. The request is valid from 41F5. And that's ADDR2 of opcode instruction register 10. Does that match what we see here? That's the branch plus. Okay, so we're adding the wrong value to the opcode, to the operand. Let's check why. The request. Okay, so let's mark where an opcode starts. So we have an opcode starting here, and this opcode is a fetch from 41F4, which is the incorrect one. Okay, so we're interested in the instruction before. So we search for the previous fetch, which is here. And that's the instruction we're after. That's the instruction we want to analyze. We fetch from 4101, and we got 10. We fetch from 4102, and we got F1. And now we expect, and at this cycle we do the sums from 03 and F1. Why 03? Because that's the next program counter. So those are correct. And now let's also follow the ACR carry. We called it ALU ACR. Let's follow that as well to make sure it gets the correct value. Okay, so ALU ACR is 0 on cycle ADDR3. ADDR3 is this one. So we were supposed to execute this. However, ALU result is F4. So the next fetch is from 41F4, which is correct. 41F4, except now it claims that it wanted 40F4. And I don't see that in the test program. Branch plus, F1 is the operand. There was no carry. Okay. I'm sorry. Okay. This is where it gets a bit confusing. So here's the thing. We've got two values that we're adding. We have the branch destination, which is signed. And we have the current PC, which is unsigned. So the math here is a little wonky. Let's break that down. So let's do an example. The example we have here is a PC is a something 03, and the offset is F1. So F1 is negative, which means that we need to, we had one of those open already, somewhere. F1, if we reverse all the bits and add 1, is minus 15. So we need to subtract 15 from 0,3. If we're subtracting, but if we just add it, we see that there is no carry, right? We get F4, no overflow. Because we're mixing signed and unsigned, our logic needs to be a little different. To illustrate that, let's do the opposite example. Let's say PC is F1, and so if in this case, we should update the high. But let's look at the opposite example. The opposite example, PC is F1 and offset is 0,3. So the answer is F4, and that's the correct answer. We don't need to update the high. So in order to understand whether we can start a new instruction at this point, we need to ask ourselves whether we're adding or subtracting. Usually we don't need to ask that question when we're doing 2's complement arithmetics, but in this case, we do need to ask that question. Right. So what is the answer? The first thing we want to look at is the sign bit of the instruction of the operand. Now we have the operand in DL, and now we need the DL to be connected to the decoder in order to be able to look at it. So that will require a new line. Okay, so we want input DL7. We want bit 7 of the data latch. And then we go to the code, and we have decoder, and we'll do DL7 in gets reg DL data out, and we want bit 7. Okay, so this will do this hookup, and now we can look at DL bit 7 to check whether we need to subtract or add. Let's make sure that we hooked it up correctly. Decoder DL7 is hooked up to a register, register 6. Okay, that's probably okay. Now what do we do with it? So strangely enough, this does not affect us in this cycle. When we do the addition, we don't care. We only want to look at it when we actually check whether we need an extra cycle to adjust the program counter high. So what do we care? If I had it here somewhere, if the offset is negative, we want to make sure that there is a carry. If the offset is positive, we want to make sure that there is no carry, right? So in this case, we don't need to update the program counter high, and we don't need if there is no carry. If there is a carry, if we add 1, 0, then the result is 0, 1, and we do need to update the program counter high. So If the offset is positive, we can start a new instruction if there is no carry. So DL7I, not DL7I, and not ALU carry, or DL7I, so the offset is negative, and this is the bit that is confusing, it confused me. If the offset is negative, we want there to not be a carry. So in this case, sorry, if the offset is negative, if there is a carry, it means we do not need to update the program counter high. So if the PC is 03 and offset is F1, there is no carry. The reason there is no carry, there is no carry, and we need to update. If the program counter was bigger, so if the program counter was 13, something 13, and the offset was F1, then the result would be 04104. So we'd have a carry. Now, what you'll notice is that this carry means that the subtraction remained within the same page. It's a bit confusing, I'm sorry. It's just the way it is. So what we want here is that if it's negative, so either it's not negative and there is no carry, or it is negative and there is a carry. Thing is, this very complicated logic has a simpler, which is not DL7I XOR ALU ACR. So the XOR is one of them has to be, exactly one of them has to be 1 in order for the condition to be set. And we want the negative. So either both are 0 or both are 1, which is exactly what's written here. Actually, this is clearer, so we'll leave it like that. And that should take us through this cycle. Let's make sure it compiles. Simulation. Run. We are at 52. We did not perform the branch plus. Let's see what went wrong. Okay. No, okay. Actually, everything went right. We correctly identified the condition, but we didn't say anything to do if it happens. But we'll do it in the next cycle. So, CADDR4. What we need to do now is either add or subtract 1 from program counter high. It's a bit annoying, but at least we know which, because we have DL7I. So we need to add 1 if DL7I is positive, so the bit is 0, and we need to subtract 1 if it's negative. So if DL7I is negative, else okay. The good news is that we get an extra 6502 cycle to do that. So we can actually ADDR out PC, just so it doesn't complain about the about being idle. Okay. If the offset is negative, it means we need to subtract 1. let's begin with the positive offset. If the offset is positive, we need to load the program counter low, the program counter high somewhere. So we need, actually we need that unconditionally. We need ADH source to be PCH ADH. So we're loading the program counter high onto ADH, but you notice that ADH isn't connected to the ALU. Now I can load it also on the data bus, and that is connected to the ALU, but it's connected on the wrong point. So I'm not going to do that. Instead, I'm going to use this pass, which I think isn't implemented, but we'll implement it. What this does is it allows me to pass values between the buses. So I can say I want the special bus to hold whatever the address bus high is holding. And I do this with SBADH. So I set a control signals CTL SBADH to 1. And like I said, I think that one's not yet implemented. SBADH. Yeah. What you'll notice is that we have something that takes the special bus and puts it into ADH, to address bus high, but we don't have the opposite direction. Thing is, the opposite direction is a bit problematic because if we have both directions, we have a loop with no clock in the middle, and FPGAs really don't like that. So the opposite direction is going to happen with a register that uses the clock. That introduced latency, but we're fine with the latency. In fact, we can do that in the cycle before, and then we won't even need the latency. The ADH, PCH ADH, and SBADH. And then we just copy the way I did this to the data bus. So special bus and what we have here is ALU result. Zero SB, no, not interested. I thought I did that to the data bus. Apparently I didn't. Okay, so we add a new SB source. Which is called, we don't, yeah, we add it, but we don't actually implement it. So we call it, no, that's the DB source, sorry. Here it is. SB source, and we have DLSB. And we called it SB. Ah, no, sorry, that's a control signal. Okay, sorry, I'm sorry. I'm a bit, okay. We have, let's look at the OSFF we have. Not this one. ALU result, not this one. Data bus latch, data bus. Here we go. This is the same thing for the data bus. So, this data bus latch stores the last value that the data bus has in the previous cycle. And we do the exact same thing for the a special bus latch is special bus let's just store it next to the special bus. Okay, so we have a source called special bus latch that stores the value the special bus had on the previous cycle. Actually, that's the wrong one. Address bus high. That's the right one. ADL latch. ADL latch is the ADDR bus high. Okay. And now we can say that the SB source has ADLSB, and ADLSB is ADL latch. So now we added another source to the special bus, which is the previous clock cycle value of the ADL, which we can now set here. SB source is CTL ADL SB. We don't actually need this. The very fact that the address bus has the correct value means it's now available to us here. Of course, it's ADH SB. So the very fact we had it available here means it's now available to us here. And now the special bus will have the correct value. So that takes care of the B input, of the A input. Now we need to take care of the B input. We want to add one or subtract one. So we need the data bus to have zeros. Sounds strange, but I'll explain in a second. So the data bus actually can have 0, and that is called ODB. So we want a SB and we want DB SRC to have CTL ODB. Semicolons are something we should use. Okay. What does a 0 help us? Because it seems like I just added 0 to the program counter high, which doesn't sound very productive. However, if I set the carry to 1, which I can by doing control signals I add C, I think that's the one. Yeah, I add C equals 1. What the accumulator will do, the ALU will do, is assume there was a previous calculation that overflowed, which is correct, right? And add 1 to whatever result I gave on the inputs. So I gave it program counter high plus 0 plus carry, and that will give me a +1. So the inputs here should be a B decoder ALU B source is CTL DB ADD. So that takes care of adding one. How about subtracting one? Well, subtracting one, we're using 2's complement logic. In 2's complement logic, minus is reversing all the bits and then adding 1, which means that -1 is a value with all the bits set. We already have the data bus with all the bits clear. If I just run it through the inverter, it will give me a -1. So I just say the carry is 0 and the dB bar add. And this should give me a -1 on the program counter high. Let's see if that even compiles. So we got to 53, which is a certain advancement. And the ALU result is not correct. Okay, let's see what we did here. Because I didn't tell. Oh, sorry. I need to tell it that we're doing an addition. And this time the ALU result is ADDSB, FC, ALU op sums. Where are my markers? I didn't, sorry. Okay, so ALU result is 42, which is test plan, not correct. It should be 40. So what went wrong? DL7I. Let's see if DL7I was correct. Decoder DL7I. Let's put it here. DL7I was 0. The reason it was 0, we already had this problem last time, is because I was reading the program counter here. No, because I was reading the program counter here, and that invalidated the data latch. So what I need to do here is to tell the control signals not to update the data latch. This is a dummy read. I don't want the actual value. And this should solve this problem. So, yep, and the ALU result is 40, exactly as it should be. Cool. The next step, and with that I think we're done, is store the result in the program counter. I mean, that's why we did the whole thing. So, C ADDR5. We want, again, it's not the way it is. Let's look at the control. PCH, ADH, PCH. Okay, so we want several things. We want the PCH to get its value from the special bus, so that's SBADH. And then we want the a program counter high to get its value from ADH. Sorry, we want the special bus to get its value from the accumulator, from the ALU. So we want the ALU result to go to the special bus. We want the special bus to go to the address bus high, and we want the address bus high to be loaded into the program counter high. And this should update the program counter high, which means we're done. We can go on to the next instruction. Let's see how that works, if at all. Yeah, I said if at all. You can jinx me. I said if at all. ADH-PCL is not declared under the prefix. You're right, because it's ADH-PCH. That works. So let's see if the simulation works. No, let's see what went wrong. Expected 40F4 received XXF4 on cycle 53. So we got the fetch. Did we get the fetch? No, the fetch is now here. So that's, and that is removed. And this fetch, so the program counter got the wrong value. Okay, so let's see why. Program counter PCH got the wrong value. The address bus high was the wrong value. The special bus was the wrong value because it happened on the wrong cycle. ALU result. So at this cycle, ALU result was 40, which means that on this cycle, special bus source, we did the cycle too early. At this cycle, the result arrives on the special bus one cycle later than it does to the rest of the system. So all we need to do is to see ADDR5, nothing. $53. No, still not correct. So let's go again. ADDSB. The special bus is getting XX. Okay, let's verify what I just said about the correct cycle to do that. So we want the special bus inputs. And this is the ALU result. And the ALU result gets loaded from the ALU result async. So 4.0 in this cycle in ADDR5, we are supposed to load the result. We are loading in ADDR6. Okay, so let's try again. SB source is ADDR SB, ADD SB. So that is the correct. So at least the special bus, if we're in ADDR5, should get the correct value. Let's see. So here we are. ADDSB, the special bus get 4.0. And now the ADDR bus, if I can just find it, ADDR bus high is ADH invalid. And it's PCH ADH. Why is it ADH invalid? ADDR high. Okay, that's correct. ADDR bus high. We needed to set it to SBADH. So, set this special bus to get the ALU result. I'm not sure what SBADH does. Okay. And now, ADDR AD decoder. ADL, ADH source is CTL ADH. So now the special bus gets the ALU output, the ADH gets the special bus value, and the program counter high gets the ADH. And we are on cycle 61. We actually managed to pass this hurdle. Let's just check what cycle 61 is. Cycle 61 is branch equal, which I think also should have worked, but let's begin with this one. I think that's enough to say let's stage for commit. So we added a control to push the ADH to the special bus. We added 2 inputs to the decoder, the flags and the DL7 and the 7th bit of the data latch. We added the logic to hard code the relationship between the instruction register bits and which flag it is that we're looking at. We added the branch instructions. We added keeping the ALU carry around. And this is the implementation of the branch instruction. And this is the top level connection of the inputs and outputs we added. And the new latch we added. Okay. Let's have a look, because as far as I'm concerned, the branch equal was also supposed to work. So let's see why that didn't work. The first thing I do is make sure that this is in fact the 0. Yes. Okay, so are we tracking condition flag? I think we're not. Decoder. Condition flag is under decoder, and yet, not here it is. Okay, that's not a good place. Let's put it above instruction register. Okay, run again. So, we are on the fetch instruction here. And with the instruction we actually fetched is for C. Okay. For C. Yeah, I think 4C is a jump, which we have not yet implemented. So actually, yeah, we got the branches. We probably got the branches working at this point. If not, we'll find out about it later with in the execution. So commit a branch opcodes, all conditional branch opcodes, and push so that you guys can grab it too. And I think that's a good place to sign off for today. Thank you all for joining. I really appreciate it.